So we'll look at section 3.7 and the concept of related rates. So we will be looking at how two variables will change over time and how those changes in time relate to one another. So before you get started on this video, you might want to go and review some key concepts. So two key concepts that you might want to review is one, the concept of the chain rule, and then two, the idea of the implicit derivative, or differentiating implicitly. So something to remember is that we have two derivatives on this page, dy dx, and we have dy dt. They are similar, but they are not the same. So dy dx is the instantaneous rate of change of y with respect to x. Likewise, we have the instantaneous rate of change of y with respect to t in this derivative. In this section, we will see y's and x's, but we will be differentiating with respect to t. Now, why can we do that and how that all works together? Let's take a look at an example of just a simple equation that relates y and x. We look at an equation like y equals sine of x. Here you see a relationship between y and x. But what if we had another component to this that is hidden from our sights? And that is that y is changing in relationship to time, and x is also changing in respect to time. So we have both of these variables, and they both depended upon t, but x and y are related to each other. So what is the relationship with respect to how they change in time? And so we want to see how their rates relate. So if I take the derivative of both sides with respect to t, well, the derivative of y with respect to t is going to be dy dt. Now the derivative on the right-hand side with respect to t, well, we have the derivative of sine function, and that will be a cosine function. But we're differentiating with respect to t this time. And so therefore we're going to consider x to be a function of time. Now you don't see this variable t anywhere in here. So this is why we have the concept of implicit differentiation coming up. Is x is an inside function, so I'm going to differentiate that inside function with respect to t. So this gives us an equation where we can see how y changes in time and how x changes in time, how those rates relate to one another. This is the concept of going from an equation to another equation using implicit differentiation that we will use in this section. So just like we had back here, this equation, y equals sine of x, that was kind of our governing equation, and then from there we could take the derivative. So we're going to be looking at word problems. And these word problems quite often are going to give us quantities that they tell us, and then quantities that we are supposed to find. And so the initial steps are going to be, you want to find an equation, and that equation that you're going to look at, likewise, we want to write that equation. And to write that equation, oftentimes a sketch is going to be helpful, and labeling any quantities on that are fixed. We only label fixed quantities. And then after we get that equation, that's when the calculus comes in. We can take that equation and then apply the chain rule, taking the derivative of both sides with respect to t. Once you have that, then you're going to be able to go back and fill in any specific values that are appropriate to the scenario that you've been given. So what do we mean? Let's take a look at an example. So here we're supposed to find the rate of change of the distance between the origin and a moving point on the graph. So one thing I want you to notice about this graph is this point is not fixed. It is moving in time. It is moving along this path, and this path is given by our equation y equals x squared plus 1. Now we're supposed to find the rate of change of the distance between the origin and this point. Now, this point is moving, is not fixed, so we can't label it, say, 5 comma something, because it is moving. So, how do I find the distance between this point, the origin, and this point? Well, let's call that distance capital D. Now, I'm not going to use lowercase d because I see too many lowercase d's whenever I take derivatives. So we'll call it capital D. So what is that distance? The distance is from one point to another point. So let's label this point. What do we know about it? This point, the x value is changing. And also, the y value is changing. But what is the y value for that x? Well, if I want to know what the y value is, I plug x into x squared plus 1. So that point is given by x comma x squared plus 1. And as x changes, the y value will change in relationship to that. So let's come up with our governing equation. Capital D squared equals, and now this is the distance formula. I have the difference of my x's. We can even draw a triangle if it helps. This distance is x. And what's this distance? It is x squared plus 1. So if I look at the triangle then, I have d squared is x squared plus x squared plus 1 squared. So now we have an equation that relates d, distance, and x. So now that we have our governing equation, we can differentiate this with respect to time. So with respect to t. So let's take the derivative of both sides with respect to t. Okay, so now, how in the world do we take the derivative of this? Just like before whenever we did implicit differentiation, remembering that x and capital D are both functions of t, time. So, if I take the derivative of d squared, I'm going to take that exponent, bring it in front, and I obtain 2d. Now, that would be the derivative with respect to d, but I'm not taking the derivative with respect to d. I'm taking the derivative with respect to time. So therefore, I have to treat d as an inside function. So d being the inside function, I need to take the derivative now with respect to t. Likewise, x squared. I have 2, and then the derivative would be 2x, and x is now my inside function, so dx dt plus, now this one's got layers to it, I have x squared plus 1 quantity squared. So there we go, it's going to be 2 times x squared plus 1, now raised to the first power, and then I take the derivative of the inside. But the derivative of x squared plus 1 is 2x. But again, we remember that x is an inside function. So we have yet another layer to this, and I take the derivative with respect to t. So here we have 2d dd dt equals 2x dx dt plus 4x x squared plus 1 dx dt. So this is the equation that relates the rates. See dd dt dx dt, and we have an equation that relates those. So now we can look at our specific scenario. And our scenario gives us some information. We have x equals 5 and dx dt equals 2. So those specific moments are only used after we obtain this equation that relates our rate. So let's remember what we were supposed to find. In this equation that we've been given, or that we've just found, we have several variables. We have capital D, we have dd dt, we have x, and dx dt. So that's 4 different quantities, but I see 2 of them up here. If I'm going to solve this equation, and I'm supposed to be solving it for the rate of change of the distance. So that rate of change of the distance is this quantity, dd dt. That's the unknown that I'm trying to find. But to find that means that I know all the other quantities in this equation, which is okay because I know x is 5. dx dt is 2. So I have the right-hand side completely taken care of. But there is one more unknown, capital D. So I can use this picture or this equation, however you want to do it, to look at the specific scenario when x equals 5. So let's look at when x equals 5. If x equals 5, we know that d squared will equal 5 squared plus, and now substitute in x is 5 into x squared plus 1, so that'd be 26 squared. And so d squared equals 701. So d equals the square root of 701. And time is measured in seconds. So let's determine what dd dt is by plugging in what we know to be the case. So we know that d is the square root of 701. We do not know dd dt, and that will equal 2 times, and we know x is 5, and we know dx dt is 2, plus, and then again 4 times 5 times 5 squared plus 1 times, and then dx dt is again 2. So this gives us 2 square roots of 701 dd dt equals 20 plus 1040. So simplifying the right-hand side some more, and then solving for dd dt, we obtain 530 over the square root of 701. Now, this means whenever we write our final answer, since it's a word problem, we should write our answer in words. The distance is changing at a rate of 530 square root of 701 over 701, because we had to rationalize the denominator, centimeters per second.